Welcome everyone to this presentation related to RISC-V security verification using Perspec and portable stimulus models. This work is a collaboration between MediaTek and Cadence Design Systems. I am Kiran Kumar Palla from Cadence and I am here to present this work on behalf of the whole team. Here is the flow of today's topics. I'll briefly touch base on the importance of security verification in general. Then I'll dive into a specific verification problem, elaborate on the specific requirements of a hardware security block and related verification challenges. After that, I'll explain how we address this specific verification problem or challenge using Perspec tool, libraries, and portable stimulus models. Security verification is important to ensure that the hardware and software components within the SoC are designed and implemented to protect against malicious attacks and security breaches. SoCs used in automotive, mobile, and data center applications could be vulnerable to attacks that can compromise the confidentiality, integrity, and availability of the data and systems. More importantly, security verification can also help identify potential vulnerabilities and security weaknesses in the SoC design. Security as a concept is very broad and deep. In this presentation, we'll deep dive into an aspect of security generally found in modern designs. All modern SoCs have multiple memories and resources that are shared by multiple agents in the system. The security of the entire system could be compromised if an unauthorized agent gains access to these shared resources or memories. To prevent that, RISC-V architecture defines a hardware block that enforces accessibility policies for the shared system components. Our work is to verify that hardware security block as quickly as possible using Perspec and portable stimulus models. The next few slides, I'll go over the specification of the hardware security block. RISC-V architecture specification recommends a physical memory protection unit, PMP in short, to enforce accessibility policies in a RISC-V based system. The important job of the PMP unit is to limit the range of physical addresses accessible by software programming. PMP unit can also tackle the security aspects related to physical memory accesses and their privileges. The privileges may include read, write, execute permissions in different execution modes of the processors. A RISC-V CPU can run in 3 different privilege modes: user mode, supervisor mode, or machine mode. The PMP policies that have been programmed into the system are checked for all the accesses whose privilege mode is either S mode or U mode. Supervisor mode or U mode accesses without proper permissions will trigger access fault exceptions in the system. So there are 2 important goals in verifying a PMP unit. One is to ensure accesses with proper permissions happen correctly. Second, equally important, is to ensure accesses without permissions generate exceptions. Diving a little deeper into the PMP unit specification, a PMP unit supports dividing the available physical address space into different regions. Each region can have a different access permission policy. The number of such regions could be 0, that is no PMP, or 16 PMP regions or 64 PMP regions. So each PMP region is defined by configuring or programming two specific registers corresponding to that PMP region. They are the PMP config register and the PMP address registers. We'll look into the details of these two registers in the next slide. PMP configuration field for each of the PMP regions is just byte wide. So to support a maximum of 64 PMP regions, the PMP configuration fields are arranged in 16 CSRs. Each PMP configuration field has permission bits, that is read, write and execute permissions, an address matching bit and a lock bit. The address matching bit or the A bit defines how the address programmed in the PMP address register is interpreted. A lock bit or L bit, when it is set, indicates a specific PMP region. Registers cannot be reprogrammed unless the heart is reset. Any subsequent register writes are ignored. So the bottom line, with a combination of PMP configurations, address matching modes, the lock bit, the PMP unit enhances security by supporting controller permissions at a very granular level across multiple physical memory regions in the system. The permissions can be dynamically reprogrammed by each CPU core to enforce its own security policies on the shared system memory and resources. Let's try to summarize the PMP unit specification as well as the associated challenges in verifying a PMP unit. A PMP unit is a programmable hardware security block. It allows multiple memory regions to be specified, each with its own privilege access policy. And each CPU core can enforce its own privilege access policy in the system. So the verification of such a PMP unit is complex because of large space of concerning crosses of PMP regions, crossed with multiple cores, crossed with access policies, crossed with all bits and pieces within the access policy, permissions, address modes and stuff like that. The complexity is amplified when we cross those already complicated concerning crosses with physical memory attributes of the RISC-V specification. The PMS includes shareability, cacheability, exclusiveness, etc. So when these are thrown into the verification mix, the challenge becomes even more complicated. Moreover, it's not easy to create test cases and test infrastructure to verify negative scenarios that generate exception faults, disallows agents to access certain regions of memory and shared resources, and so on. With those challenges in mind, the next set of slides talk about our work to address those challenges using Perspec and portable stimulus models to create reusable security scenarios. This slide summarizes what was provided by Perspec PSS libraries and the overall PMP verification unit verification flow. Perspec and PSS definitely simplified and shortened our verification tasks. Basic memory operation actions are provided by Perspec PSS libraries. The required building block security verification actions are also provided by the Perspec libraries. The overall verification process involves 4 steps. The first step is to model a compute subsystem. A compute subsystem is a part of a SoC that's responsible for executing computation tasks, like a CPU. This step also involves configuring the memory subsystem to specify all the shared memories in the system. The next step involves modeling PMP features and configuring PMP regions required for the test scenarios. The third step is to develop PMP security scenarios, that is high-level scenarios to test PMP unit. This step uses building blocks from the previous two steps. Finally, we generated a lot of test variations to expand the PMP feature coverage. Modeling compute subsystem using Perspec models involves supplying required design data for Perspec PSS libraries in table format. These are usually CSV tables or Excel tables. Two of the important tables are shown on the slide. A processor info table captures all the CPU related information. It has an entry for each core or agent in the system, its type, associated cluster name, IDs, and other details are filled in. The next table is a memory info table. It captures information related to all system memories. The table has an entry for each memory, its base address, its end address, and other memory attributes. The design specific info is then used to configure Perspec libraries. Modeling PMP features in Perspec library just requires a table containing PMP region information. As you can see on the slide, each table is a PMP region with its own region ID, starting physical address, size of the region, permissions, and region types. A region type column directly corresponds to the A bit or the address bit in the PMP configuration registers. Region permissions column also directly corresponds to the permission bits in the PMP configuration registers. So this is all that is required to configure PMP in the Perspec library. Another table that is related to PMP features is a table containing PMA info, that is physical memory attributes information. PMA table specifies virtual to physical address mapping for each memory block in the system. There are other memory attributes like shareability can also be specified in a PMA table. After filling out PMP and PMA tables with design information, PMP actions in Perspec PSS library can be used. Two such building block actions are shown on the slide. Switch privilege level action is an action that switches execution modes between machine mode, supervisor mode, and user modes. Another action, config PMP region, programs PMP registers based on information provided in the PMP table shown in the previous slide. There are also multiple other actions provided by the Perspec library. Some of them are a register write or a register access action, where it programs a RISC-V system register with a specific value. And there is a config PMP region, which we already discussed. It configures, programs, or reprograms the PMP registers based on the configuration specified in the PMP table. There is write data action, which is a basic action to write random bytes of data of specified size to a selected memory block in the system. There is also read check data, which reads and checks the previously written data from a selected memory block. We are now into the third step of our verification flow. After modeling the compute subsystem and PMP features, we proceed to create system-level security scenarios targeting PMP unit verification. This and the next few slides discuss some of the high-level security scenarios that we have developed. The scenario on the slide actually does a PMP write in supervisor mode. So this is supposed to be a positive scenario where S mode is able to access memories to write data into it. So the scenario has multiple steps. It enables address translations in supervisor mode by programming the SATP register of the RISC-V system. It then configures the PMP regions as defined in the PMP table. It then switches the privilege level from a machine mode to supervisor mode. That's where the PMP checking actually kicks in. So it then performs a write access in S mode. So assuming a positive scenario, a PMP region is randomly selected for access in S mode, and the memory access in S mode should have no problems. The next scenario is a negative scenario where an S mode access has no permission to write to memory, but it still tries to access it. In this case, an exception is generated by the system. The test case catches the exception and exits the test gracefully. That's because the test is expecting an exception. This slide shows a couple more interesting scenarios related to PMP unit. A PMP region overlap scenario validates the PMP privilege accesses with overlapping memory regions. That is, two PMP regions target the same address with different access permissions. It would be interesting to see the system behavior in such cases, which might even catch some corner case bugs. Another scenario is a PMP change lock. A lock bit forces the privilege access checks even in machine mode, not just supervisor and user modes. In addition to that, it also prevents reprogramming PMP configuration registers for that specific region. In addition to creating high-level, system-level security scenarios targeting PMP unit, we were also able to generate large number of tests covering various variations, including permission bits, address matching modes, lock bit, multiple CPU cores, multiple memory blocks in the system, and so on. So in conclusion, writing security scenarios using Perspec enabled us to do efficient verification of this complex challenge. Out-of-the-box atomic actions and scenarios provided by Perspec were very helpful. All the building blocks were already there in the library. They had to be configured with the user data, with specific design data from the users. That helped us create large number of test cases covering all concerning crosses in a relatively short amount of time. We were able to model both positive and negative security scenarios related to RISC-V security verification targeting PMP unit. Thank you.